an entrepreneur for a startup, which I founded.
Okay, you founded a startup. And okay.
Why we started with the last one.
Okay. So thanks, Matteo, for being here. He will give a talk on the stochastic three-body flow, stochastic resonances and diffusion in small body dynamics.
Yeah.
Thanks.
Thank you. Thank you for all being here. It's an honor to be here present his work. Conducted together with Benjamin Boschman. We were both working for ISIA. I was in IMS space. Benjamin was in Telespazio. And we decided to work together on this project. That's about bringing forward, let's say, the Poincare picture in going from determinism and predictability from Laplace. Then Poincare came and said, okay, celestial mechanics is deterministic, but actually not predictable because we have chaos. And here we're aiming at saying, actually, celestial mechanics is not even deterministic. So let's see if we can do this. The starting point is Hey, 1982, in which is stated in this abstract that actually celestial mechanics is an example of a field in which determinism cannot be assumed necessarily. So since then, a number of works attempted at modeling stochasticity in Hamiltonian dynamics in general, but particularly in celestial mechanics. It's worth outlining the work by Del Bruno in 2009 on the walk in celestial mechanics, or Idea 2020, modeling stochastic behavior in the three-body problem. So, what is a stochastic differential equation? You can see that actually we are taking an ordinary differential equation, bringing the differential of the time on the right-hand side of the equation. X is our state, the stochastic process. And added to the deterministic component, F times Pt, in which F is called the drift. We have a G matrix that's multiplied by a stochastic process, which is the most natural choice is Brownian motion. And so we have a G relating the number of Brownian motions that we are dealing with in our process. And this is related to our state, which is on its own a stochastic process via the diffusion matrix G. So the natural question is, why is this relevant for celestial mechanics? It is lemma. I won't go into the detail, but maybe it's easy to just say this, that because of the nature of stochastic calculus, in a one-dimensional system, if we have something like this, so we have A, which is a constant determining the drift, and B, the diffusion. If we have something like the product of dx times itself, in the usual case, in the deterministic case, let's say, we would have nothing because dt times dt is 0. But because of the nature of stochastic calculus, we have that dt squared is 0, dt times db is 0. But because the variance of the Brownian walk, the random walk of Brownian motion is proportional to time, we have that this one is equal to b squared dt, which is equal to b times dt. And so this has many important implications, I think, for celestial mechanics, because you see that if we have a coordinate transformation in which x is the state and y is a nonlinear function of the state, we have that the differential of the new representation of the state is not simply the Jacobian of the transformation times the same equation we had before, so this differential, but actually there's a term that's proportional to the axiom of the transformation. And this will play a role in the evolution and the diffusion of things that naturally would be integral motion. So the question is why Brownian motion is astrodynamics. Previous works we built on motivated this a bit qualitatively, saying that there's dust around the sun, and we can model this dust as a source of a thermal bath, which is not really a thermal bath in the sense that the stochastic manifestation on the particle is not due to collisions, but rather of thermal stochastic wiggles of the gravitational field that leads to something like a Brownian walk on the dynamics of the point mass. We showed this also quantitatively. We randomly sampled a plane, simply initializing randomly its major axis eccentricity, and we showed inside a disk of a certain size what is the number of particles, dust, inside it. And so via Gauss theorem, we can say that the gravitational pull coming from this disk is proportional to the mass inside it. And actually, we did a frequency analysis of the signal, which is the density inside this disk, as a function of time. And we actually found that the spectral density, this is the frequency, is kind of constant. So the assumption that the signal is actually a linear process, so a Brownian motion, seems to hold, even numerically. So we start from, before going into the three-body problem, we start from the stochastic two-body problem, which is the usual one here described in polar coordinates, in which we have two additional stochastic perturbations related to the radius of the vector. Previous work argued why this is a compelling model, and we start with this. And with this model, using the lemma I outlined here, we can see that actually the energy and the angular momentum are not constants of motion. The angular momentum in particular is easier because there's only diffusion. So the average of the angular momentum is constant, while we have the statistics of it diffusing in space. Well, for the energy is even more interesting because together with diffusion, the second two terms, here in this lemma, so this one, we have that a term is also multiplying the t, and it's positive definite. Everything is positive multiplying the t. So the energy is slowly drifting towards higher values, while it's also diffusing and the uncertainty is increasing. We can see this numerically. For these results, we use the Noether-Maruyama numerical scheme for integrating the system. And you see that for the deterministic case, beside numerical error, the angular momentum and the energy are constants of motion, while in the stochastic case, they're characterized by stochastic behavior. It seems like the financial markets, the graph of these two quantities. But they're qualitatively different. Maybe one cannot see this from here, but actually H is associated to a zero mean and E is different. You can see this here. We did a Monte Carlo analysis on the multiple realization of the stochastic process of the energy of this two-body problem. And okay, this is a numerical, but you can see that the scale here is really small and the mean is kind of constant in agreement with the symbolic expression we obtained. And for the energy, there is this small drift towards less negative values. We started with an elliptic orbit. So this was the two-body problem we started from. We wanted to go to a three-body problem to discuss basically the origin of the moon and also potential dynamics generating potentially hazardous asteroids. And so we started from this perturbation, the model of the perturbation, and we simply went from this polar representation to inertial one, Cartesian. And Ito's lemma gave us that the drift is still zero, but the diffusion is written like this in the inertial frame. Then we added to it the actual deterministic components of the three-body problem, the circular restricted one. And once again, we have to apply a transformation and this lemma again to go from the inertial to the co-rotating reference frame. And in this frame, the usual equation of motion hold, but the diffusion is made of this, in which x, r, and y are expressed in the rotating reference frame. And so we integrated these equations numerically again, and you can see that the Jacobi constant, which is not a constant of motion anymore, is characterized by stochastic behavior, which in particular is not stationary, because the transformation from the reference frames is time dependent. And you can see in the configuration space, we play the evolution of the orbit. And so we are starting still at L4. So in the deterministic case, we should stay still in L4. But because of this perturbation, we start getting excited and we go into an unfortunate trajectory, which eventually leads to an escape from the ocean and intersects the orbit of the primary, which in this case is the Earth. And so we follow Bill Bruno's work in arguing that something like this could model the origin of the moon due to an impactor that coalesced in L4, and then because of the dust around the sun was excited and left the orbit, and with a non-zero probability of hitting the Earth then. So symbolically, I won't expand the diffusion of the Jacobi constant because it's even longer than this, but this is the drift, and you can see it's time dependent. And you can see also that, again, everything is squared. So the Jacobi constant is going down, the energy is going up. You can see it here. Again, a Monte Carlo simulation gave us that the diffusion, statistical diffusion leads to an increasing in the standard deviation of the Jacobi constant and a drift towards less positive values. So the goal of this perspective in celestial mechanics was to, first of all, explain some kind of dynamics that we conjecture could exist for the Trojan population of asteroids moving from L4 to L5 in the Jupiter-Sun system, and also could lead to the formation of potentially hazardous asteroids. So maybe these asteroids could escape the ocean trajectories and enter an intercepting orbits with the Earth one due to this stochastic perturbation. And most importantly, it could explain the origin of the moon and why this object, this Mars-sized object, leaving L4, left it. So in the title, we also mentioned stochastic resonance, which is this process in which if one is starting from a double wave potential and starting here in the configuration space, it will stay here. But if you say that actually this is related to potential plus some stochastic term, then you will be excited in a way that for certain values of epsilon will make you go something like this. There's an optimal value for which you have this kind of resonance, which is called resonance. It's different from the usual way of explaining resonance in this conference, but it's nevertheless a resonance. We couldn't find it, but that's simply a consequence of Higgles's lemma, because you have resonance, you could have a stochastic resonance only if the drift is solely due to this double well potential light, double well light potential, sorry. And because the expression of the Jacobi constant for us is not only associated to the proper potential of the three-body problem, but has also a drift, an additional term, this means that it's not possible to obtain this. One could hard-code it in a way that simplifies this diffusion matrix for the three-body problem and kills the additional term from Higgles's lemma. We didn't do this because there's no physical meaning in such a model, but we expect to have something like stochastic resonance between L5 and L4 if this matrix is more sparse. So regarding future works, it would be interesting to see, and also to understand if there's something valuable in it, to see from a given stochastic two-body problem if one can compute the probability of escape. Because if the starting energy is a little below zero, the stochastic perturbation could lead to an escape orbit. The same could be done in the three-body problem. So what's the probability of impact given enough time? Also, maybe important for this context is the third point, the fact that even in low dimension, the interception of invariant Tori, which creates topological constraint for Arnold diffusion, don't exist anymore. And so one can expect something like Arnold diffusion in low dimension if there is a stochastic perturbation. I have no idea what are the implications of this in celestial mechanics, but this is in fact something that's been investigated in particle accelerators for the dynamic aperture to see what's the uncertainty of hitting the actual particle in the presence of stochastic perturbations in the form of electromagnetic noise. Finally, it could be interesting to generalize the quantification of chaos. As we try to say here, if celestial mechanics is not only unpredictable because of chaos, but it's also stochastic, it may be necessary to quantify the degree of predictability in some more general way. And so, for example, generalize the computation of the probability density function of chaos indicators like the finite time element exponent, and see if this has implications for the long-term evolution of perturbed Hamiltonian dynamics. This is it. Here are our emails. I look forward to your questions here via email. Thank you.